Chapter 17, the Fourier series. We'll have two chapters on the Fourier series. I always thought this was one of the most beautiful, simple, and illustrative mathematical ideas around. Not to diminish Laplace or any of the other brilliant math that's around. This one is one that always seemed to me to be very much visualizable. In other words, the math looks a lot like the functions themselves. The graphics and the math just kind of, intuit one another. You can look at the graphics and intuit the series and so forth. More than that, though, this allows us to decompose functions of time or functions of one variable into a series of smaller things that we can analyze individually, and it just creates a large series, and we can decide what elements of that are causing different reactions, like low frequencies causing bridges to sway versus high frequencies that might cause glass to break, that sort of thing. So let's just get into it then. The Fourier, it's a trigonometric series. Okay? This is the observation that was made by Fourier, another European, this time French, mathematician that was, as the lore goes, working on heat transfer, heat flow, and came upon this about periodic equations, periodic functions. And that was that for this is the definition of a periodic function, obviously. The function at n times some period, right? Here's the period right here. That's our period. And we're going to see that a lot in this chapter. Right? N times that period repeats the pattern, or whatever the pattern is that's going on there. Okay? And more than that, then, it can be expressed as a sequence here of sines and cosines. All right. Notice there's this constant term, and then just a whole set. So we're going to call them. We're going to label their coefficients by the a term. So every other one here. And you notice what these are. A1 has omega 0. A2 has 2 times omega 0. A3 has 3 times omega 0. Same with the sine portions. B is our coefficient, and the 1 goes with a 1 here, and 2 goes with 2 here. Okay, so these multiples are always integer multiples. And they are harmonics. Right? You probably heard that term before. I'm sure you're probably already familiar with it. But that's what the Fourier series is about. It's finding the harmonics and the relative values of each of those harmonics. So expressed in a nice tidy form, more than just being harmonics, we can look and say, oh my, here's a DC component. So in any waveform that's periodic, got to keep that in mind. It has to be periodic, even if it's strange, and the look of one period is strange. If it's periodic, it can be broken out this way. And then there's this AC portion, which is always composed of either cosines or sines or both. Okay, and it's an infinite series, right? So hopefully all the important information we want is contained in just a few of the harmonics, right? Otherwise, we're analyzing or looking for a lot. By the way, you might guess my background and interest includes a lot of signal processing, and that might give you some clues to why I really like this and find it very insightful. If this is made up of a simple summation, a decomposition of any periodic waveform, I can say, wow, if I could find those base frequencies and the first few harmonics or whatever contains that, I can extract information. All right, I can extract information easily if I know that certain frequencies are loaded with the information. And this is in fact true in just a tremendous amount of nature. It's a lot of the basis of color and color theory. It's a lot of what goes on with television transmission, internet transmission, all this sort of things. All the modulation schemes are based around this ability to have things like a low frequency as a carrier, and then multiples of that. A lot of the signal processing and multiplexing schemes are based around being able to add cosines and sines and skip some frequencies for one channel and another channel contains certain frequencies. So enough said about that right now. But so that's why this probably resonates with me a lot. To say nothing of the fact that it helps diagnose mechanical systems. You know, what are failure modes? What are passing modes? All this sort of stuff. All right. In order for this to work, it has to converge. It's an infinite series, as I pointed to here. So, but an infinite series, as we've seen before, even in the Laplace, if it doesn't converge, you really are going to have limited use for it. Probably limited means no real practical use. So it must converge, and in order for that to happen, there are a few properties, a few things that need to be. F of t, whatever function is that's periodic, right? So this is the periodic guy. Whatever f of t is, it has to be single valued every place. In other words, even if it's a discontinuous function, it doesn't have to be, right? It can be like so, but it can't double back on itself, right? This sort of thing cannot be. It has to be continuous. It has to be single valued everywhere. All right. It can have a finite number of discontinuities in any one period. If I were to make this, say, up to here, my period, and then somehow get down here and repeat the original thing, a crude effort to do that, right? I can do that. I've got a discontinuity here and here, probably here. All right, maybe at the takeoff point. But there's a finite number of those. If it's infinite, you can't keep track of that. You can't actually converge and get a true Fourier series. All right. Also has to be, notice the word finite keeps coming up again and again, number of maxima and minima in any one period. All right, one of the points of emphasizing these things right away is these things are pictorial. If you have a graph or you have like an oscilloscope pattern or a mathematical function of something, if it, you know, like that comes out of a PSpice or a MATLAB simulation or any of those mathematical tools, if you can't identify finite numbers of maxima and minima, finite numbers of discontinuities, you're not going to be able to get convergence in the Fourier series, and hence you won't get the series. But more than that, I think, is as I've used this and seen it applied in circumstances over the years, this word finite means something more than, less than infinity. I find for it to be realistic in its application, this really means a reasonable number? In practical terms, it means a reasonable number. If that gets too large, pretty soon the visualization, the connection, what terms are important, what terms are not important, becomes much more difficult to read and to keep track of. Okay, so I tend to think of finite as code language for reasonable. It's mathematical code language. And finally, the integral from t0 to t0 plus tau. So what is this thing here? This is 1 period. That's what we're integrating. And it is what? The magnitude of the function integrated over 1 period is less than infinity. No matter where you start and end, no matter where you start the period. You can start like in a cosine or a sine. You don't have to start at 0. Any periodic function, if taken 1 period over any part of, starting anywhere in the function, the integral of the magnitude of that over that period has to be less than infinity. Now this only makes sense. It almost seems odd that it needs to be stated, but in mathematical terms, and mathematicians really like to have this stuff very clear. All right. So now, the name of the game, as you might guess, is finding coefficients. If you've got a series, you've got an expansion. This is like converting a periodic time-varying function into a series of individual parts. The name of the game is going to be finding the coefficients of those various parts. So we'll begin with just finding A0 to begin with. And this is our basic equation of Fourier, what was, on the previous slide, where the f of t, right, f of t, here's what we had before. The f of t is all of this. Okay? And we'd broken that into the DC and the AC components. So what we want to do now is find A0, the DC component. If we take the integral of this over 1 period, right? This is now the new step. We're going to take the integral of both sides of that equation, which is the Fourier equation, and then break it up, right? Just taking normal mathematical steps here. So we will have the integral of the constant A0 over 1 period, right? So that ought to be pretty easy to come by. And then it's the sum of the integrals over 1 period of all the an cosine n omega t's plus the bn cosine n omega t's. Okay? But nevertheless, you can sense at this point things mathematically can get dicey in a hurry with all these cosines, these trig functions here, and integrals of these and so forth. Fortunately, just as in Laplace, there's a very nice set of common integrals. And by common, it means you're going to use these a lot in diagnosing Fourier coefficients. So let's bring up that table. Okay, this is right out of the text. These are going to be, these 7 you're going to see over and over and over again, right? Here are the first 2. We're seeing those. We're seeing this one and this one right away. Here's a product of sine and cosine. We can anticipate that coming with different n and m's. Here we have sine and sine with 2 different harmonics multiplied together. Here's cosine of 2 harmonics, right? These 2 are, right, product of the harmonics, of the same harmonic. I'm sorry, different harmonics. This one is the same harmonic. It's not. None of these are. They're just, sorry, product of harmonics. All 3 of these. Right, all 3 of these are product of harmonics. Here it's sine, cosine, sine, sine, and cosine, sine. You can imagine these are going to come up a lot. The bottom two here are the squared functions of a given harmonic. And we know from dealing with enough trigonometry, we're going to hit those quite a bit. All right, so what's going to happen in this one? Well, right off the bat, these first two are the sine of a harmonic over the period. All right, any harmonic over the period. And it's 0. All right, now is that a shock? Well, it shouldn't be, come on. If you have this as your waveform, which for the moment we do, if this were the sine, this would be the period. And what does the integral do? It just simply takes the area under the cosine, or the sine, and that area has an equal amount of positive and negative to it, right? So that, of course, is going to be 0. Right, so those two evaluate quite easily right away to 0. That's really what this statement is right here. All right, what happens next? That means the function of t, what started on the left over there, is now reduced to this much. Right, but we can see this coming. This is a dt, right, which is a0 t evaluated between 0 and t, and of course that is a0t. Right, pretty nice. So far we're dealing, now everything is reduced to constants. So where does this go? A0, solving for that, is simply 1 over the period, right? So this is the inverse of the period, times the integral of the function over that period. All right, and you can imagine if the function itself is a single-valued sine wave, then the DC offset is 0, right? And this will just prove that out. All right, how about some other terms? Following up with our cosine, this part of it, right? The cosine, the integral of the cosine, f of t times the cosine. So I should actually be clear, we're actually going to try to solve for the cosine coefficients. And we're going to do that by modifying or just taking our f of t and multiplying it by various harmonics of cosine omega t. Okay, so we can vary m. So we're going to do that to both sides. Here we've just taken the Fourier description and multiplied it by cosine m omega 0 t also. Just did the same thing to both sides, okay? Now the next step is clearly just expand that, right? Multiply it through, and what have we got here? Our coefficient, which we now know, don't want that, our coefficient that we now know over one period times the integral of cosine over that period, okay? Then we've got a summation of a whole lot of multiples. So you can already anticipate that table. I'll bring it back because we're going to need it. Here we've got the product of the cosine of two different harmonics. And here we're going to have the sine times the cosine of two harmonics, right? And we don't know if n and m are equal or if they're different. Here there is no product. So let's bring back our table as it fades in from the background, and let's take a look at it piece by piece. Right? We know the first term is just a constant times the cosine integrated over a period, and that is 0. Right? So that guy goes away. This whole thing has become 0. Right? Then we just keep working down our chart. How easy could this be? We integrate over the period B sub n, the sine terms, times sine n omega t, right? That's just a term straight out of the Fourier series. This, straight out of the Fourier series, times our cosine n omega t. And what have we got to say about that? Well, the sine times the cosine, right, is integrated over a period is 0. Now you might want to look at some of these. You might want to gander at some of these for yourself. Do a graphical interpretation here. Just to assure yourself that some of these are true, because these are really powerful statements, right? They're saying, look, things are going to be 0 or they're going to be some constants depending on the period, right? So this is very powerful stuff, and here are going to be the important things. When are the harmonics the same or when are they different? So those are very powerful, and they're fairly easy to see graphically if you don't want to actually do the math of all that. What's next? Oh my! Now we look at the terms here. Oh, I didn't complete this this idea. Where am I? Yep. So these all go to 0. Isn't this lovely? So far we have nothing to show for our effort. So now we're hoping, and we will see, of course, that the coefficients on the cosine terms are going to be 0. They're 0 if m and n are not equal. All right. So what are we going to be reduced to? It looks like we're going to come down to this one right here. Right? These are the sine terms are gone. We're going to come down to that one where we end up with cosine squared for each of the terms. We're going to come up with cosine squared for each of the terms where the harmonics are the same. All right, and that's this straight out of there. So we evaluate the left side now at cosine m omega 0 t, and we have, that's what, a sub n of tau over 2. So this is going to be easy to evaluate. Remember the condition here. They are now equal in this one case. Right? This was our left-hand side, so let's not lose track of it. We evaluated here. This was the right-hand side, but now the left-hand side, because of all these zeros here, the left-hand side is brought back into play, right? This is our left-hand side. But we now know it's equal to a constant. Isn't that something? Big help there, because now we can solve for an, and it is 2 over t, the inverse of that constant, times the integral of the function times the coefficient. And this would be repeated for every n, every harmonic. Right? And you can imagine you would do this process in evaluating the coefficients until what? Until this guy here became so small, right? And then you end up with a very small number times 2 over tau. But the prevailing thing is the 2 over tau is always going to be there, right? So you can kind of see how this is going to break out to something, some expansion that's a 2 over tau times a whole bunch of terms. Actually, this would be out here, 2 over tau times a whole bunch of terms, just a summation of a bunch of terms. All right, I think we have, so yeah, there is more than one way to skin a cat, as it turns out. We have the traditional method, and probably the most used method for finding the DC, the cosine coefficient, and as you saw at the bottom, the exact same process leads you to the B coefficients for the sine terms. But now there's an alternate method why one would want to skin a cat. I never knew, even at the time of the phrase. I haven't heard the phrase in forever. I never knew why you would do it. I still don't know. But we can express the function as our DC term, right, which we have. And now instead of sines and cosines, we've still got the summation. We want that. But now we're going to take cosine of the harmonics and a phase angle, right? So this gives us a single term to go after, and we'll make it a capital A because it's now going to represent, basically, it's a vector, right? You can see this coming. It's a vector. So with the help of this trig function, right, the cosine of two terms, so our alpha here is going to be n omega 0 t, and our beta will be our phi sub n, okay? So with the help of that, we're going to rewrite the left-hand side, right? So all of this good stuff right here is ready for us right here. And on the right-hand side, then, we break that up with the help of this. So here's our first term, right, the A0. And then it's the sum of A sub n of cosine of n times cosine n omega 0 t plus or minus the sine of A sub n sine of n sine of omega 0 t. All right, now you recognize what's going on with this, right? This is a magnitude at an angle, right? So we're right back to where we were with the old power considerations, right? A phase angle and let's not say power factor again, but we're back to that type of thing. So this is another way of interpreting it. And we will still have, so I grabbed this from before. We saw this before. There's our DC and our AC terms, right? Only now we've got our A terms look like this, right? This out of this guy, right? Now it looks like this. And it's A cosine n omega t. And the B terms are our A sine n omega t, right? So this is just recognized. This was always present. It's not like, oh, some new thing. This amplitude at a phase angle has always been a possibility because that's inherent in what's going on here, right? For any given n omega, we would have, let's say, a cosine term. We'd have a sine term of size bn and a cosine term of size an. And now we've got this new thing here of capital A of n, right? So we're just breaking it down that way. Okay. Here you see what I just drew, right? It's the A sub n is the square root of the sum of the squares, and the angle is the inverse tangent. Okay. All right. You can think of it this way. It looks like I drew it upside down relative to this because I didn't pay attention to the minus sign, but the picture is the same. All right. So the frequency spectrum of a signal then consists of the plots of the amplitudes and phases of the harmonics versus frequency. Simple statement, obvious statement, but it needs to be made because people often talk about frequency spectrum. And the important thing that commonly gets lost in that discussion is that they're harmonics, right? And I think, by the way, in the lab on our scopes, a lot of the modern scopes, you can actually get the frequency spectrum, and you'll see it. But it's often so fuzzy and stuff because it contains harmonics of harmonics and harmonics of second and third things. So they're not necessarily periodic waveforms. But so just again, tables are good. Some things are easier when you have cheat sheets. And here's a simple statement of that. So the values of the cosine and the sine, handy to keep this around, okay? The cosine, these things right here, like these integrals, we've had these around, and it's important to keep them around. All right, so we have these in our tables of stuff. Now, we will be doing Stuff Open Book. You usually always have reference to books and stuff, but if you have to go thumb through pages to find these, I'm just saying here, don't be afraid to keep the cheat sheets handy. You'll find your favorites. At various times, I've just made copies of them or extracted copies and kept them, handy for me in a folder rather than having to page through all the pages of stuff. Good to do. All right, I want to move ahead now to another important aspect, which is symmetry. The thing about periodic functions is if you can spot any patterns in them or any regularities or routines in them, it makes it easier to model. It makes it easier to extract what are the important components. Symmetry is one of the main things we look for. There are 3 cases of symmetry that we're going to consider. Even symmetry is a reflection about the vertical axis, and I'm going to go through each of these one at a time. Reflection about the vertical axis. Odd symmetry is an anti-reflection, or I'm just going to call it an inverse symmetry, again about the vertical axis. And then the half-wave symmetry is a form of odd symmetry, except it works where the reflection is, or the symmetry is around the half period instead of the full period. And we'll go through each of these cases here. Let's start with even symmetry. Okay, the definition of it is quite simple. Remember, this is reflection, just a mirror image around the vertical axis. So it simply says the function in negative time is identical to the function in positive time. Here are pictures of that. All right, you can easily see this. You can easily see this symmetry. If this is this is my axis of. My hand is cockeyed here. Hang on a second. I got to erase this. Let's get our eraser in action. I so seldom get to use this. Not that I don't make mistakes, but it's just easier to press ahead. All right. So this vertical axis, the axis of symmetry, I'll be more careful this time. You can see how any value here obtains the identical value there, and there. All right. Notice something else about this. Before we even leave this first picture, it kind of looks like a cosine, doesn't it? Right? Kind of looks like a cosine. Now, this second one, which has the same symmetry, now notice how that splits the positive part right down the middle. So this point equals that point, and this point equals that point. So all of this obeys the even symmetry formula. Not quite as easy to see that there's a cosine wrapped up in this. I just suggested this in the first picture because as we discuss even symmetry, we shouldn't be surprised if we find out that it's rich in cosines in its end. All right, here's one that has a 0 axis value, right here. You're sitting at 0 for the axis. But the symmetry is good, right? This point right here is the same numerical value as that. Go down another period, same numerical value as that. So here you're sort of left to think, well, what's the period? It looks to me like one hemisphere is the period. So maybe we'll have to take it as 2 hemispheres for the period to exhibit even symmetry. All right. So when we do this, we can see that the the integral of even symmetry, and they've added this little subscript down here, the integral of even symmetry is over the whole period, right? The integral over the whole period is the same as twice the integral over the half period, right? So, oh, I'm way up there. It's equal to twice the integral over the half period. That's characteristic of this function here, right? If it's truly that way, then you need only take the half period integral and double it. Okay? That said, you can see that the value of the DC part of it is going to be, this is the old formula, nothing new here, and we'll take the integral from 0, so the half period of f of t dt. Okay? Remember, it was 1 over t before, over the whole period. Now we're just doubling the half period. We're invoking this to our 1 over t. All right, the cosine values, right, were 2 over t, so now we're doubling those to be 4 over t, and we go through all the cosine values. And in the way that I just described to you, we could go through the math and we'd find out that the sine values will end up 0, right? So it's a cosine-rich waveform, even symmetry. See, there's something that comes out of it kind of right away. All right. So let's actually do some of this to gain some confidence. I just sort of stated those things. So we're back to this, which was our definition or our derivation of a0, right? 1 over t times the integral over a period of f of t dt. So that is this. If we now just apply this idea, let's break it up into two parts, the left half and the right half. All right? And let's just carry it out from there. So then it's 1 over t times, we'll do a substitution of x for t so that we, we then have minus dx. So we're substituting what, x for minus t, or minus x for t, if you want to say that. And then from 0 to t, we'll keep that part. And this then amounts to 0 to t of f of x dx, right? Getting both of them going from 0 to t. And 0 to t over 2, sorry, t over 2, not t, of f of t dt. All right. So that's just simply, this is the same thing as this, right? These are equal. So you're just doubling this. Okay? All right, let's do this for an. So an is now, we start with our old formula, but now we've broken it up into two parts, the left half and the right. Okay? And after doing that, we can say that any an is 2 over t. This was all from before, right? From our table of handy integrals. Okay? So we're going from 2t over 2 to 0 with the substitution of minus x for t, right? So this was t, got substituted. Here's minus x. There it is. And so it's minus dx. This remains the same. Flip it around, right? So we're doing t over 2 to 0 of is f of x. So remember we have the original thing of f of t equals f of minus t. So that's all we're invoking here for x. And we get this changes to this. Cosine of minus x is the same as cosine of x. So we make all those substitutions and keep going. And we now have two things. If we, instead of minus dx, we go to plus dx and reverse the limits, we have the same thing again. This side equals this side. And so we double it and get 4 times instead of 2 times, and that's our values for a of n, okay? Finally, we want to convince ourselves that the sine terms are really gone. So let's do that one. Start in the same way, right? We're going from minus t over 2 to 0. And we go through all of that just as we got done doing, making the various substitutions. Here we have the f of x gets substituted because the minus is the same as the plus, right? But now we have sine of minus x is what? Minus the sine of x, if we want to extract that. So that minus turns this minus dx into plus dx. So that's how this all comes together, and the minus signs seem to magically disappear. But now if we reverse the limits, this and this, if we reverse them, we have to add this minus sign in order to do the reversing. Right? So it's just sort of follow the bouncing minus signs. So now we have these two things. Oh, look, it's the identical function. This much equals that much, except we have a minus sign playing against a plus sign. So, of course, this equals 0. All right, so we've convinced ourselves of that. But again, go back and look at the pictures and sort of recognize, ooh, that triangular wave centered around 0 feels a lot like a sine, a lot like a cosine. And indeed, that's how it's going to be. Odd symmetry. We can move a little faster now. Odd symmetry is like this. The function on the other side of time, of the vertical axis, the function at minus time, right here, is equal to minus the function at time. So where is that? Here, let's just take an easy point. Okay, this point at minus time, go over here, is also the minus value. So it moves down there, right? Take something else. Here's something on plus time. If I go to minus time, I'm where? This is, I'm right here, only now I go down here. Right, so that's what's going on. Here's a nice square wave. And notice these things really just got moved in phase, so you can kind of see the phase difference between this and the early one. So this corner is now down here, right? These 0 points are those minus points, are those positive points. So these are examples. Here's one that doesn't, it looks periodic, but it's not quite as regular as these other guys. A lot of 0 space in it. But the important thing is, this corner moves down here, so it obeys the equation. Okay, getting used to that. The setup looks like in these first two, if I'm to say the same things I said for even symmetry, this looks like it will be sine wave rich, right? So let's do that. The function of the function over a period for f0, right, when n is 0, is 0. So our a0 is going to be 0, right? That's what we're seeing here. And you can see that in every one of these cases, even though it's not the limit of the cases. But it does say our DC offset is going to be 0. All right, and just by visual argument, I was arguing that the cosine, there'll be no cosine terms. And the sine terms will look just like the cosine terms in even symmetry with the new 4 here. And the function times each of those harmonics. All right, so we can go through all that step by step. It follows very similar, in fact, the same arguments as the last time, except notice now, if we track through all the minus signs, here's our f of minus x, sine of minus x, but we just have to be careful to note that f of minus x is going to be minus f of t, right? So we don't get the nice cancellation that we got before. So the sine of minus x is going to be minus sine of x. That's wonderful. It's going to take this out. So this is positive. This is now positive. But the for this to be f of x, back up here, we've got to have a minus sign. So here we're putting that minus sign in, whereas before that kind of disappeared. Okay, so now these are the same, just like in the last argument, right? And you get 4 over t. All right, same arrangement. All right, we can pick this apart more carefully if we want and look at the odd and the even pieces. So if we have, let's say we have neither even nor odd symmetry, but quite often we can decompose, right? This is a thing that's not even or odd, but it can quite often be decomposed into an even and an odd set of functions. Okay, notice what we've got going on here. This is even symmetry between this and this being expressed. This is odd symmetry being expressed. So we can decompose it into a set of even and odd symmetric equations, right? Some function can be decomposed into even and odd. And then we know once we have even and odd, of course, we can press on with what we know. So let's do that. And if we can then treat, if we can find these, so the first trick is going to be what? Finding an even and an odd function whose sum, the sum of these two, makes the function we started with, or the function we want. All right? But we get better at this with observation and learning. So let me take this moment then to say, here's some useful properties of odd and even functions. This is sort of like, why are we doing all this? Well, some things you need to know. The product of two even functions is also an even function, right? You may remember from way back in just basic numbers and so forth. If I take the product of two even numbers, you always get an even number. That's sort of nice to know. It's a simple sanity check. Same thing is going on with even functions. If I multiply two even functions, I get an even function. The product of two odd functions is an even function. Ooh, now that's not the same as numbers. If I multiply 3 times 5, I get 15. All of those are odd, okay? 3 times 7 is 21, right? What else? What's 3 times 15 then? 45. Things remain odd. So, but in this, the product of two odd functions turns out to be even. We're not going to work out all these. These can all be worked out. Actually, they're probably, some of them might be intuitive at this point from all the tables of nice trig functions that we've been producing along the way, or lighting up along the way. So the product of an even and an odd is odd. Okay, that also isn't like numbers. 3 times 4 is 12, so not the same. So you need to think of these. There are some similarities, but not all of them. But like numbers, it's good to sort of keep these in mind. What should I expect? The sum or difference, that is, of two even functions remains even. That's like integers, right? Two evens, add them or subtract them, you get an even result. The sum of two odd functions is an odd function. That's different than numbers, all right? And the sum of an even and an odd is neither even nor odd. Ooh. So 6 things. And the first 5 just kind of tells you with products and sums, all the combinations, 2 evens, 2 odds, and an odd and an even. The first 5 are predictable. If you take the sum of odds and evens, that's not predictable in its result. But a lot of help there, because this goes back up to the top here of this decomposing I'm just going to call them tough functions. Okay, you're going to have to be doing this. Half-wave symmetry is the final symmetry. What is it? Ooh, this looks difficult. So if I take the function of time at the half period, then not only is it flipped, but it's the inverse. Okay, so we've got this thing going on. It's the minus of the function is the half. So let's look at some pictures of this. Let's take the function of t. So I'm going to pick an easy point here. This one right here, halfway in there. And the right-hand side tells me, take the negative of that. So go down here. And that's going to be the function halfway over here. Actually, I probably should have done this the other way. Right, so that's going to be the function here, where these 2 points are equal, and they're what? T over 4. Roughly, this is T over 4. Okay, so just a way of saying this, right? So you could, just as an example, let's go here. So our F, we plugged in what? T over 4 for our time, minus T over 2. So that was equal to F of minus T over 4. And that's equal to minus F of T over 4, right? So this was our starting point right here. This was our guy right here that we started with. And he's here. And if we negate that one, right, then we negated him. And then we went backwards to F of minus T over 4. We negated him. And we put it back here at that point, right? So that's literally in that picture what was happening with half-wave symmetry. Here's another one. Now this doesn't suggest sines or cosines explicitly, right? This one kind of does. This second one here looks a lot like a sine wave with the edges squared off instead of round. So let's see what happens. Okay, but we can see here's this corner, whatever it is, and I go down and back to that place. That's back here. So that's the half-wave symmetry thing going on. Here are the values for it. There's no DC component. There are both AC, there are both cosine and sine components. Okay, but look what's happening. The even components, the even harmonics, where are they? Right here. This is what I want you to observe. The even harmonics, right? Even harmonics are not there in both the cosine and the sine, right? So there's no even harmonics. Okay? Again, an important observation. So this is made up of odd and odd, right? So we might remember from our other side what we're going to get. Odd and odd gives us even when we sum them. Okay, so we can pick out properties like that. That's all I'm going to say is this for observations about half-wave symmetry. pretty much amounts then to working out a lot of problems and seeing these things. I really emphasize getting a strong graphical to mathematical sense. So we'll spend some time on the oscilloscope with this and try to get some good ideas. Another one of these cheat sheets or tables, the effects of symmetry on Fourier coefficients, right? If I have even symmetry says there's no DC component, right? That's what's going on here, no DC, right? If it's even symmetry. I'm sorry. Whoa. Get out the eraser. Saying this backwards. Here there's odd and half wave. There's no DC. Okay. In even symmetry, there is DC. There definitely is DC. We saw that. We derived it, for goodness sake. All right. There is also no sine wave in even symmetry, right? And it's all cosine harmonics. All right, and you can just look and see the opposite. In odd symmetry, there's no cosine; it's all sine. Right? This is what we've got. We've got no cosine. Half wave, you've got what? No even harmonics, right? No even. But you've got both odd harmonics. Okay? Kind of watch it, and there's some remarks. So here's some common functions, these charts straight out of your book. But I bother to reproduce them because you'll look and see, I'll go on to the next page, which has the rest of them. All of these are real basic handy ones to have. So let's take a moment on them. Here's the standard square wave, and here's the standard pulse train, right? Now, notice tau here. You don't know what tau is. Tau is free to be something else. So when you go to most signal generators, you'll see you can vary this distance. Right here, they're equal. It's a standard square wave. Whoops, and this, and this are equal. Now, if I change that to be a pulse train, I can change this, right? This is t minus tau. All right. Here's the sawtooth, common. Oh, and here's the triangle wave, right? Also common. So these are standard ones. And why are they common? Why do we like them? I can tell you one reason. Because when you go over to the Fourier series, they contain a set of frequencies that maybe you want to examine. For instance, I might have my my circuit that I'm working with, right? Here's my box, right, with my H of S. And I want to know what this circuit does when I poke it with certain harmonics. This is a common deal. I want to poke it with certain harmonics. And in fact, maybe this model is an electronic model of a bridge or some mechanical system. And I really want to know, what frequencies does that respond to? Well, rather than sit and dial up every frequency and the magnitudes and all that, by going to a chart like this, I can say, look, if I just hit that thing with a square wave, I know I'm going to have these frequencies in it. If I mess with the square wave and make it a pulse train instead, I've still got my sine waves, but they're multiplied by cosines. I'm going to have a mixture of harmonics, right? This is where a lot of this comes in. It can be very involved in modeling and this sort of thing. Here I've got one that says, so go back to this for a moment. You can see here I've got a DC component if I use a rectangular pulse train. But if I shape that all the way up to be a square wave, the rectangular, I mean the pulse train goes away. I mean the DC component goes away. So just simply, I mean, you can imagine in a lab setup, just simply dialing the tau, the pulse width, I can change whether there's a DC component, I can change the content of the signals. All of this stuff really becomes handy when we start modeling circuits and circuit responses and use circuits or circuit type equations. This is all around differential equations and signal responses and stuff. So this is why when you look at your signal generator, you will see more than sine waves available on there. Usually squares and triangles are there as well. And so here, we've just done the square. You have the sine wave for individual components, but now here we are able to invoke triangles, sawtooths if we want. And what's the point? Wow, this says if you want only sine wave components with a DC offset, choose me. Right? Good ways of testing, good ways of stimulating. All right?